So without further ado, our first presenter is Nortek's very own Principal Sales Engineer and Product Manager, David Velasco. David has been with Nortek since October 2013, but has been working in the Doppler technology world since 2002. He has been using ADCPs since 1999. Recently, he headed the development of Nortek's newest and smallest ADCP, the Nortek Echo. Today, David will be discussing methods for estimating suspended sediment concentration using acoustics, as well as some of the unique technology created for investigating suspended sediment. I will open the floor to you, Dave.
Okay, awesome, great. Thank you very much, Caroline, and thanks for everybody who worked to put this together. I know everybody is, had their share of Zoom meetings, but we hope that you will stick around with us today, and in this that will be an informative time for all of you. So again, just wanted to say welcome once again, and let's get started. Today we're going to be talking about, well, at least in my presentation, I know Dave Toppin's presentation also will be a very nice complement to what I'll be introducing here, as I will cover some of the theory, and I'm sure David Toppin's presentation will also will go into more details on some specific application that he's been working with for quite a while. So yeah, let's get started. So I have to start first with a basically a brief I would say a disclaimer that this presentation, it's not necessarily about showing how to measure the sediment concentration using ADCPs. So you should stick around towards the end for David's presentation, will be later today, and because he's going to be more focused on that particular application. This presentation, however, is going to be an introduction to the general concepts and the limitations of using acoustic technology for sediment characterization. And I'm going to try to attempt to offer some guidance on these for those who are interested in this topic, and provide some examples of some of the data that we have collected. Now, we start with the basic formulation of what is called the Sonar Equation, which has, comes in many different flavors and formulations, but I'm writing it like this, where we have a relative backscatter, and which is the intensity of the return echo as measured by the ADCP, and that's equal to the source level minus twice the transmission loss, twice because the acoustic pulse is going out and then coming back in, plus what we call a target strength. And these have historically been referenced by capital letters like I have here. Now, this equation has many components that I'll try to explain here now, and also has some very critical assumptions that we need to know about. Now, we'll start by source level first, and which is what is sent by the actual ADCP itself. And just as another side note, here, of course, we're focusing on ADCPs because that's the topic, and of course, that we want to, that of our expertise is in. But keep in mind that a lot of this theory was really developed before ADCPs really existed. And so they were, some of the things, of course, are transferable. But here we'll be using really as from the point of view of sound generated by an ADCP. So now, again, going back to here to talk about source level. Source level is what is sent by the ADCP. Now, generally, these values that are rarely provided by manufacturers, it's not really needed for velocity measurements. The source level is assumed to be known and is assumed to be constant throughout time, which is our first big assumption in the process here. But just again to cover, we have transmission or transmit power, which is the amount of energy that transducer puts out, the efficiency of that transducer, and directivity index, which is essentially a measure of how focused that transducer actually is. The third component here is the what we call target strength, and that is what the information that is needed from the sediment itself and its characteristics such as size, distribution, the sphericity, level of flocculation, and many others. Now, these again are all assumed to be constant throughout the measurement volume and assumed to be constant throughout the measurement time, so then homogeneous and uniform in space and time, which is again another big assumption that we have to keep in mind in all of this. The part in parentheses here is to address that the particle, quote unquote, is actually a cloud of sediment, and, but the theory is based on individual particles. In the middle parameter here in the Sonar equation, this formulation of the Sonar equation is what we call transmission loss, and that is what is needed from the medium itself. In other words, that the water plus the sediment mixture. Now, this is more variable, so I'm going to talk about it more in the next slide. Now, later on, all of this is rearranged, and we try to be and we want to solve this eventually for the logarithmic of the suspended sediment concentration. Finally, I just wanted to note that target strength here is a parameter that is probably one of the main reasons why people who have been using the same ADCP and going back to the same location time after time have actually been quite successful at using ADCPs for sediment work. And Dave Toppin's presentation will cover more of that. But it also means that the people who have just taken, just the core concepts and applied to varying locations or with multiple types of ACPs, without sort of really buttoning down all of these assumptions, maybe have not been so successful at it. Okay, so moving on out, we're going to just go back here. We'll expand now about this transmission loss parameter here. So the transmission loss is, I think, the most interesting to sediments using acoustics because it has the largest influence and it's more variable. So it has, really its own slide here, like I have. The three parameters in the equation handle the following: the geometric spreading, which is this first section here, the absorption by the water itself, and then the attenuation by the sediment that is in the water. Now, geometric spread, as you probably have already heard or seen an illustration similar to this one, this means that the signal, it gets diluted with the distance from the instrument. And so that needs to be corrected so that the intensity of the signal is independent of how far away the measurement volume actually is. These alpha terms over here, they are the attenuation coefficients, both for the water and for the sediment itself. Now, these can be modeled, but in practice, they're probably best estimated from actual measurements themselves. Now, there's been a lot of work that's been done since, I'd say, probably the 1930s on attenuation coefficients. And today, the attenuation by the water itself is fairly well understood. But it's a function of, I would say here in the order of importance, first the frequency, then salinity, then temperature, and finally pressure. Now, for suspended sediment attenuation, the alpha sub S there, parameter, it's a bit more complex as it is very heavily dependent on the particle size and distribution among other factors. It's also a rather implicit situation that we have there because you need to know first the particle size and distribution in order to estimate then later the particle size of distribution acoustically. So there's a bit of a catch-22 there. But to give you an example, here is some work that was done by Mark Landers in the USGS, which was focusing specifically on suspended sediments that are commonly found in river environments in North America, in where he had proposed a combined model that addresses both fine as well as coarse particles. And to expand on this, and here I have from a paper by David Toppin, again, who will be presented in a short while. Here I'm showing the attenuation coefficient curves calculated for different concentrations on the left here, and showing a similar pattern to what we see on the graph on the top right. That is basically a decrease in attenuation as a function of increasing grain size for fine particles, but then increasing attenuation after particles increase in size from clays to silts. On the right bottom graph here, from this reference, it shows how different frequencies respond differently to grain size, especially around the clay silt transition zone, which is really important for many applications. So you start seeing some of the complexity in all of this, and it's not just a simple matter of just plugging in numbers on equations and a magical value popping out. One important point that we just wanted to highlight here is that in most cases, suspended sediment concentration here is less than 1 gram per liter. And so the transmission loss is dominated by geometric spreading and absorption by the water itself. That is the alpha W parameter that I have listed here. Okay, so I know you might be thinking to yourself, wow, this sounds really complicated. What do I do? Well, in the words of a famous Doppler man, the most common method is simply to ignore the problems and hope for the best. But of course, we can't all be, sitting at the beach and, just enjoying life. So because we can't do that, we have to address some of these issues somehow and understand some of these assumptions and limitations. And if you review the literature, you find that this has been approached in one or two different ways, which I'm calling here a semi-empirical method or an acoustic theory method. And there's been, of course, variations on this and combinations of these. If you in what I'm calling the semi-empirical method, basically means that suspended sediment concentration is is collected. Actually, physical samples of the water and the sediment are collected and co-located acoustically with the acoustic signal, that is, and then a model is developed that relates the two. So basically, it means that relative backscatter is a function of the suspended sediment concentration times some type of calibration factor. And this would be again along the lines of what David will be talking about. Whereas the acoustic theory method here basically tries to capture all of the variables and then compute an attenuation coefficient, which can then be calibrated against a known suspended sediment concentration. We don't have time to go through all of the advantages and disadvantages of both, but I'm listening here just so you can have some basics. Again, the empirical, what I'm calling semi-empirical method is fairly straightforward to do, but is not directly transferable between sites and instrument, or at least not easily. While the acoustic method is, of course, founded in very solid footing, but can be quite complex to do properly because there are many parameters and many assumptions that go into this. And so that's why, sediments with acoustics, it's very hard to get a very straight, black and white answer to a lot of this. So we're trying to just show you some of the highlights. So what can we do? Well, we have some problems and we have some consequences to deal with here, right? Now, in general, there are poor range resolution for most ADCPs. And what we mean by that is that the cell size only get down to a certain length. So you cannot see smaller variations than what the cell size is. For those operating in a down-looking setup, it's difficult to get data close to the bed due to a side lobe interference. So it's difficult to properly compute sediment flux, for example, because you miss the area with the highest concentration, which is along the bed. And of course, ADCP ranges decrease when the concentration is high. And so you can miss data when things start getting really interesting or the concentration starts really going up. And of course, there's a lot of instrument variability, especially on older systems. And so it's hard to have a one-size-fits-all approach to all of this when it comes to ADCPs in this application. I'll just check here, how am I doing time-wise? So what we at Nortek have done in order to overcome some of these limitations, well, I'm talk here a little bit about for uplooking and downlooking applications. What we have done is added a fifth or a vertical beam, which points straight at the boundary. You can see here in this particular case, this is a signature 1000. So we added a beam that points straight at the boundary, so that it right away eliminates the side lobe interference. We have also added high resolution sampling of the signal strength, high resolution in the sense is down to the actual millimeter size increments, and which allows for greater visualization capabilities. And this is what we call the echo sounder mode in the instrument. And also the dynamic range of modern systems now have certainly improved, as well as the stability of the signal between instruments themselves. And what you see here in the images are on the left-hand side. These are data from a bottom-mounted, in this case, signature 1000, looking upwards. And on the left-hand side, we see the acoustic intensity of the signal from the slanted beams, which are the ones on the outside here of the instrument. And what you see is that, I mean, you can see the general patterns, but they generally lack resolution. And, of course, you start missing more information towards the surface of the water column here due to the side lobe. When you do this with a vertical beam and using an echo sounder mode, you can see clearly how you have a whole lot more detail of the water column. And again, these are data collected by the exact same system at the exact same time. The only difference here is that the graphs here on the left come from the slanted beams, whereas using just the standard signal strength from the slanted beams. And on the right is the vertical beam using the echo sounder mode. So you can very clearly see how we can get a whole lot more definition and resolution in what we can visualize out of more modern systems. Here's another example. And this is what from a signature 500, so a 500 kilohertz system. And this is a system that was mounted down looking from a surface buoy and sampling at a fairly high rate at 2 hertz. And here I'm showing 4 graphs. So we'll start here on the bottom 2, which is the speed and direction of the water. So this happened to be in the southern part of the Chesapeake Bay. And what you see here is, the tide changing, of course, going in one direction, going another direction, and then going, flipping back as the tide is changed. You see quite a bit of shear in the water column. So the top part of the water column and the bottom part of the water column are doing 2 things quite differently. And then moving up here, this is the signal strength from the slanted beams. And on the top is the echogram from the vertical beam, which is the case, again, looking down. And a couple of things that I think are, this is only about 18 hours worth of data here. And a couple of things that I think that are interesting to know. One, obviously, the resolution, the spatial resolution that you get out of the echo sounder is significantly higher than what you get out of the slanted beam. So you can see a whole lot more detail. But I also find it interesting that all of the near bed, or most of the near bed information, which you have the highest concentration, is effectively missing from the actual amplitude or from the slanted beams. Mostly because the sediment towards the top is actually getting attenuated, and then the signal isn't really getting down to the bottom as well as it can. So, for example, all of this information over here is effectively lost over here, similar to this part of the tide here. So clearly some benefits there that can be gained with more modern systems. Now, the final example that I wanted to give, this is just a study that our colleagues in our Dutch office have done. And this has just happened to be the coast of Netherlands. we're talking about some data that was collected in this little passage right here where that red dot is. So this is a about a 10-day, I'm sorry, a 17-day deployment. I'll show you here about 10 days worth of data from an up-looking signature 1000 system that's here on the left, using 25 centimeter cell size. And then we, at the same time, we also had a down-looking system mounted on the vessel, identical system mounted on the vessel, but sampling faster with much higher resolution, and of course with the echo sounder mode. And so I'll be able to show you here how these two data sets come back. So here's some of the data. Now we start first looking at the data from the down-looking system, which is the one here on the bottom of your screen. You can see how the bottom here, of course, the actual line where the bottom location actually is at about, and here it's only about 17 minutes, I mean, or days out, I'm sorry, 17 minutes of worth of data. Now, a lot of what we see here near the surface is not really concentration over here, but rather just a function of the components that we mentioned earlier in the Sonar Equation, so that we can, so what we can do is take into account the transmission loss, absorption, spreading that I mentioned earlier, and then we can get a different image, which is this one showing up on your screen right now, which is actually the direct output of our signature VM review software. So here we still see the main features, but now more related to the log of the suspended sediment concentration. So although this is not, it's not suspended sediment concentration itself, because there hasn't been any calibration, we're much closer to reality now than before. And now here's the data from the up-looking system. This is taken from our ocean contour software. And here, of course, we missed the near bed data due to the physical installation height of the instrument, but we do get data very, very close to the surface itself. And the same corrections here have been done that allow us to compare these two instruments. And from here, we can start making some more accurate inferences about what's actually going on with the sediments themselves. I think that kind of wraps it up. If this sounds very complicated, just keep in mind that you really have to still take a lot of water samples if you want to get to the next stage of actually getting concentration. Take some water samples. You have to do a proper calibration against those for your particular site, and then don't forget all of the assumptions that are implicit in the Sonar Equation, because there's a lot of variability out there in terms of sediments and actually environments themselves. And so before you can go and sit out there on the beach and relax, you just have to keep in mind these components. But if you do that well and you do them, you eventually will be able to get quite a bit of data out of ADCPs. And that is all for me. Hopefully I didn't go over time, or let's see how I'm doing, but yeah, that's it.
Awesome. So there are a few questions in the chat, Dave. The first question is the relative backscatter same as the volume backscatter variable we get in the MATLAB output file?
Short answer is no. And I'm assuming the volume backscatter, you're probably talking about the ocean contour output. But the short answer is no, because there are some of the things there that were not being accounted for. What is, if again, I'm making an assumption that you're talking about what the output from the ocean contour, there the transmission, not transmission loss, but the geometric spreading is accounted for there. And we do account for the noise, but not the transmission loss, because we don't know what water that they actually is in.
David, actually, this was my question. This is Ashwin Gadgil. I'm a PhD student at Texas A&M. Hi. So
Hi.
We did these measurements with a signature 1000 vessel-mounted instrument, and it using the echo sounder mode on it as well. So it had the echo sounder active. So when I take the echogram data and export it to a MATLAB file, it pulls up a volume backscatter variable. So that was my question. So the relative backscatter that you mentioned here, is that the same as the volume backscatter I would get from the echogram output data file?
So again, the short answer is no. Go back to probably, oh, keep going. There you go. So we don't know what the water component is here. And so we can't account for all of this in that. All we're doing there is taking account of primarily the attenuation by the geometric spreading, so that essentially is unrelated or independent of how far away from the instrument or the instrument that you are doing. I see here that May from our Nortek BV office is commenting here as well that there is an estimate for water loss in the ocean contours. So that's good to be added there as well. Thank you.
So then I'm guessing the target strength component is still not accounted for, is what you're saying?
Well, yeah, target strength, we don't know what the sediment is, right?
Okay, that makes sense. Thank
you.
So
yeah, you're again, in going back to the last slide there, you're still not going to get away from, if you really want to get down to concentrations, you're still not going to get away from collecting water samples.
Okay, thank you.
Okay. We have time.
There was another question there. Do you want me to just read that one, Caroline?
Sure. Yep. You can go ahead. I have a few private ones, Dave, but I can send those to you in an email after everything, or they can contact you in either the breakout rooms or via email directly. But you can go ahead with that question.
Yeah, no, it was asking, are you more this vessel then near the upward look? Yeah, that's the short answer is yes in that particular time. The part of it more, but is also moving, well, not of the data set that I showed, but also, did some transects along that.
Okay, great. That is actually perfect timing. So thank you, Dave. We will. Yep.